Today, I'm here to talk about modeling service networks for community resilience. And I'll mainly be talking about public sector applications of service networks. And you should expect to learn about network optimization models for locating vehicles on a network applied to public sector OR applications, and OR standing for Operations Research. And this will be a lot better if you ask a lot of questions along the way. I know the recording and I'm mic'd up, but I will make sure to repeat your question so everybody can hear it. And it will make it a lot more fun for me too, because I don't know what you know and what you're interested in. So as you probably note from this slide, I have an unauthorized picture of Bucky Badger, our mascot, driving an ambulance. You're not supposed to change the picture, so don't tell anyone. But I work in the area of emergency response, so mostly ambulances and fire engines responding to 911 calls. So all of my research has been in the public sector in one form or another, and that's sort of my inspiration for today's lecture. So I've worked a lot with service networks of public safety leaders. I wanted to start by giving a background into service networks for public sector operations research applications. Right, so I know some of you might be in different places, you might have had different prereqs, but I want everybody to learn a little bit about the application today and how it all fits together, and that should give you some ideas of how to take the knowledge that we discussed today and apply it to other settings. So the simple definition is public sector operations research is a problem whose outputs are subject to public scrutiny. Okay? So there's a few different classes of these types of problems. So the public health and safety is the area that I know most about, so it's in boldface, and that's the only one I'll be talking about later today. This includes police, fire, emergency services, and public health. Second area is community development, such as planning and transportation. Third area could be human services, which could include public assistance, welfare, drug and alcohol treatment, homeless services. And the fourth could be nonprofit management, right? So it doesn't always have to be public resources. We could just looking at the outputs that are subject to public scrutiny. And so a lot of nonprofits are involved. And this could be community-oriented programs. I have some examples of some of the types of applications that we could include in this. Later on, I'll just be talking about basically ambulance response and also fire engine responding to calls. But in public health and safety, this includes firefighters, police officers, paramedics, and post-disaster response and recovery. So these are the types of service networks that we might be including in our models in this area. And so I'll specifically be talking about location models for locating vehicles and designing response districts. Okay? This is one of many problems that we could study in the public health and safety area involving service networks. Community development could include school buses and library loan networks. So vehicle routing problems for bus schedules is a common application. Who knows about vehicle routing problems? Okay, I see a couple hands, right? So we have to route the buses in a very efficient way. Who had a horribly long bus ride to school growing up? All right, some of you know this is why we need optimization. It should be more efficient. I read a really cool paper a couple years ago on library loan networks and interlibrary loans. And again, how do you come up with the routes so that you can efficiently have a single driver deliver all the books to people that want to check out library books? I'm a big fan of interlibrary loan. I'm constantly requesting things, and I think it's a good use of my tax dollars, and I love getting the books, and I love reading them when they come in. Human services could include public assistance and programs like Meals on Wheels. So you could look at staffing models here to schedule employees, or staffing models to look at volunteer shifts. Right, so volunteer shifts often look very different from paid staff because you can tell your paid staff to do things that you can't tell a volunteer. They might not volunteer anymore. Right, they're just there for free. But those are types of applications that we can use for service networks. And finally, nonprofit management, which can include things like humanitarian logistics, a lot of volunteers in the nonprofits, and blood bank operations. And you can look at multi-commodity flow models to deliver relief aid. All right, so these are different classes of optimization models that could be used to model service networks and public sector OR applications. And they're all over the map. So I wanted to get into the Wayback Machine today and talk about how this all got started. And it's kind of interesting. I don't always like to have a slide of a bunch of old white guy, so I do apologize for that. The history is really interesting, and it started with President Lyndon Johnson. I just actually visited the LBJ Museum in Austin last month when I was visiting, and I found it really inspiring because he ran on the Great Society, was his platform, and he introduced a lot of public assistance programs to really help educate people, get them out of poverty, improve public safety. And he was a real fan of that, and he started this Commission on Law Enforcement and the Administration of Justice, among many other things. And this was back in 1965. And he really wanted to systematically study these social issues. And one of the things he did was to have a commission, the Commission Science and Technology Task Force, right? So this is like the real scientific part of this commission. And Al Bloomstein, who's at Carnegie Mellon and is really inspiring to see talk, started working on that. And what they started doing is using systems models to just model the criminal justice system. How do you get in? Where do you go? How do you move through the system? Where are the off-ramps? And they had, for the first time, an understanding of what it was like to go through the system. And it kind of started there. Right? There's a lot of excitement on using science for applications such as law enforcement. We're using science to try to put a man on the moon. It seems like it should have had other uses. And it was actually applied very broadly to public sector problems. So this is not the only type of problem that operations research was applied to in the 60s. It was applied to many public sector problems. And one project was very instrumental in this, and this was the RAND Institute partnered with the Fire Department of New York. And it was a really great partnership. And just some city administrators were willing to give math a try. And we're letting math overcome some of the politics. And that doesn't happen nearly enough. And it was interesting because there was a lot of fundamental research that was being done. The research was influential. It led to a number of reports. It was put into practice. It was actually used to cite fire stations and send them to calls. And it led to a lot of great research. It was published in the top journals, and a lot of the projects actually won the top awards in the field. Right? So this is one of the books written by Richard Larson called Urban Police Patrol Analysis. Okay, you can't read that. But it did get one of the top awards, a Best Publication Award. And a number of people were trained on this. And so Margaret Brandeau was, I think, one of his early students, and she was known for working in healthcare now. And also Linda Green, who's at Columbia. She's still working in public sector OR. Right? So it's kind of like a golden era for all this. Anyway, I like jumping in the Wayback Machine because it's kind of interesting. And so a lot of the models I'll talk about today kind of go back to this early time. In terms of these early public sector OR models for public safety, there were a wide variety of models that were developed, published, and put into practice. So the one we'll talk about today is kind of based on the set cover problem. How can we cover the most number of calls with just a few ambulances? So we get these set cover problems. I'll introduce this later on. Okay, so we've got location problems and optimization, discrete optimization. We also have queuing models. So spatial queuing models needed to be developed to look at the queuing applications. When you get a call for service and you respond to a 911 call, it's a queue. There's not usually a long line in this queue. Somebody's available to respond immediately, but you do have a queue, and your servers here are spatially located. And so we have questions like, what is the probability that our first choice ambulance is unavailable for the call, right? So that the really close nearby ambulance that's stationed right there, if it's not available, I'm going to get us a longer response time, and I'll have to wait a little bit longer. And models were developed to answer these types of questions and help us evaluate the design of the system we had. All right, so we have discrete optimization, we have queuing. We also have Markov models. So in a lot of these 911 call problems, you're always balancing the patient that's right here, or somebody asking for a fire engine, the fire that's available right now, with the potential future calls that could arrive. And you want to keep the system pretty prepared and to be able to respond to future emergencies. And so Markov decision process models are helpful for this because they look at sequential decision making. So how many fire engines should we send? So if you send too many, you can be really vulnerable in the near future. And finally, data analytics. So before computers, people were collecting data by hand and asking questions such as, how far will a fire engine travel to a call? And they would just collect data, do some ride-alongs, and you can see they plotted it out, and they had simple models to evaluate response times. Okay, so I'll talk mainly about locating service providers today, but there's a flavor of these, a variety of these types of models in different application areas that were published. All of these papers are from the 70s. All right, so I'm going to start with a simple motivating example. At the end of today's class, you'll get some ideas about how to maybe extend this to more realistic scenarios. But this might be a good time to stop and answer any questions that you might have so far. All right, so ask later if you have them. All right, so we have a fleet of ambulances. We have a staffing model, and let's say we have S ambulances that we want to locate on a network. So I have a region here, and there's a bit of a heat map, if you can see, where the brighter the red, the more calls for service. You can see a lot of calls here throughout this area, and all these blue words are the different stations that are available. Okay, so we could send ambulances to street corners, but we don't really want to do that because it's not very fun if you're working to have to sit at a street corner when you could be in the station. Okay, so we want to start by locating ambulances at station. Our second assumption is not really an assumption, it's just we have data that says different locations produce more calls than others. The third one is a bit of a dubious assumption. We will assume deterministic travel times. So it always takes the same amount of time to travel from point A to point B. Okay. And then the fourth is, for right now, I'll assume all my ambulances are available all the time, and I never have to get into that situation where I have to consider backup service. We'll lift that later on today. All right, so I'm talking about covering calls, and I'll talk about what I mean by covering a call in just a minute, and why I'm covering calls. All right, so I've got an anatomy of a 911 call. Okay, so it starts with an emergency. Somebody calls in and places a call. It's usually a 911 call, but not always. 911 call is placed. If somebody picks it up and they answer, this is our call taker. They do some triage, and then the next thing they do is they send an ambulance. And so for our purposes, that's when time starts. This is when our service provider will have to respond to the call. They're sent to the call. They are en route, and then eventually they arrive at the scene, right? So that's that box. It's a different blue color because that time is special. That is the time at which we measure our response time. Okay, so it goes from when the unit is dispatched to when it arrives at the scene. And then after the ambulance arrives at a scene, they do quite a bit of work, both immediately at the scene, and then they take the patient to the hospital if the patient wants to go to the hospital. So most times they do, but not always. Okay, so all EMS systems, and EMS is emergency medical service systems, all of them are evaluated according to the response time. Usually public sector problems are notoriously messy and they have unclear objectives. The great thing about fire and EMS systems is they have a really clear objective, and even though they're run at the local level and there's thousands of these departments throughout the country, they all have the same flavor objective function, which makes it a little bit easier to approach and to model. Okay, so what is this goal is in response time. So they basically give you full credit or no credit. There is no partial credit in responding to a call. And the most common response time goal is 9 minutes. Did you get there under 9 minutes or not? Okay, so if you're plotting this out, and you have your response time here, and then you have some utility function, it's either 1 and then it drops down to 0. Okay, so you'll notice that you'll get full credit if you respond in 8 minutes and 59 seconds, or if you respond in a minute. And it seems like you should get different amounts of credit for those two scenarios, but this is the reality. And this gives us a coverage objective function. In my evening talk tonight, I will offer you some more thoughts on this, because I've thought deeply about the coverage objective function. But right now, we'll just sort of accept this as the way it is. And I've accepted it, mainly because the service providers love it. And you know why? Well, it's easy to measure, right? So they have the software to evaluate how they're doing, and it just collects a bunch of times and has a bunch of timestamps in it. So they can very easily measure if they get there in less than 9 minutes or if it takes longer than 9 minutes. It's also very intuitive. So they want to reach 80% of all their calls in under 9 minutes. And if I tell you that, oh, they're responding to 70% of their calls within 9 minutes, they have a sense for how well they're doing, for how well the system is improving when that number changes. And it's very unambiguous, right? Response times are sort of obvious to everybody, all right? But this is what we'll be working with later. And they won't talk about changes to this, but there are alternatives we can look at. All right, this is another good time for questions about how emergency medical services operate and what their criteria are and what you don't like about response times.
Do they self-report their response times, or how do they
That's a great question about do they self-report response times. It's all time-stamped and it's sort of self-responded. Sometimes there are sensors on the vehicle, like when they leave the station it'll click on, but a lot of times it really is the dispatcher that's pressing a button. So they are slightly dubious in that you can see in the data if they forget to record them, for one. But sometimes they'll be pulling up to a location and they'll say they arrived, but they really haven't arrived per se. So it's they're a little squishy. That's a really good question. Any other questions? Mm-hmm.
So the response time is very important, and I know that depends on a lot of things, like how far is the location of the station from the people in need.
Right.
So is there any way that you can predict the traffic, because that's a big factor?
Yes.
Can you use like outside software such as Google traffic analysis that tells you like this road is like huge traffic, but you can use another one, or people from another station can get like faster response because the traffic is better?
Oh, right. So that's a good question about response time. Yeah, some of the more sophisticated software will give you estimated response times. I'm not exactly sure how all of them estimate that. They quite often use historical data. And the service providers have really great intuition too about kind of where the traffic is all the time, and because they respond to so many calls over the year. So they actually figure things out pretty quick and don't like to stop and look it up on their phone in real time. I'm always amazed at how good their intuition is. Any other questions?
Does this response time include just arriving on location or like unloading of equipment and stuff as well?
It doesn't. It is just pulling up to the house. So you can imagine if the call was here, they might wander around the building for a few minutes first. And that's definitely a limitation. It is not the response time from the patient's point of view. All right, so we're going to talk about facility location models for this. I'll talk a little bit about the intuition. I know some of you have had different courses in the past. So I'm going to give my pitch for location models. So we are motivated by locating ambulances today. I do want to mention that historically, fire and EMS go together. They're in the same department. Emergency medical services came about as a branch of the fire department. And most departments are combined today, but not always. In Madison and in my hometown in Middleton, they're separate, as they are in many big cities. So you'll see a lot of times, you'll see fire trucks responding to calls, just part of the system. So you can imagine locating different types of vehicles on a network too. It is done at the local level. I have a picture of the whole United States here just to be a little confusing, but this is a location model where you're locating some kind of hubs. And then we want to locate our ambulances or locate whatever. This location models have a lot of applicability, such as sort of close to all the demand in the system. Okay, so we want to achieve, so we're locating things. Could be ambulances, it could be stations, warehouses, shelters, hubs, and so on. We usually have to balance two things. One is cost. Of course, we want to keep our costs down. And the other is some level of service. And so I mentioned that you want things to be really close to the stations or ambulances that you locate. So we want to do those two things, which gives us basically two levels of decisions: where to locate, and then this, so the location problem and then the allocation problem is assigning our demand to those open stations here. And so it's sometimes called the location allocation models. All right, so I want you to learn about locating ambulances, but also how to apply the models more broadly. And so of course you can use these for other types of applications. I mentioned locating ambulances and fire engines at fire stations. We can also locate airline hubs at cities, blood banks, hazardous waste disposal sites, hurricane shelters, fast food restaurants, public swimming pools, schools, bus stops, and vehicle inspection locations. Can anybody think of anything else?
Distribution centers.
Distribution centers, that's good. We're going to talk about the 4 classic models, 4 location models, and then we'll look at extensions beyond that. So I have my picture at the bottom. And so the first one is a P-median model, which looks at locating your P facilities. So in this case, I don't have a cost or I don't have a budget. My budget is, at this shift, I have maybe P ambulances to locate. And I want to locate them in such a way that the demand-weighted distance is minimized, right? So I want to have as much demand very close to those stations. And if certain areas generate many more 911 calls, those should count more. And that's the intuition here. The second one is called the uncapacitated fixed charge location problem, where I can have as many facilities as I want, but I have to pay for them. So I have this kind of demand-weighted distance idea, but it's really a demand-weighted cost. And then I have this fixed cost for every time I add an extra facility that I locate to the network. So at some point, I have a big penalty from locating too many facilities on the network. For example, I'd love an ambulance located in every neighborhood, but that would be cost prohibitive, so I wouldn't do that. The third one is a P-center problem. This one minimizes the maximum distance after locating P facilities on our network. And the fourth one is my favorite. It's a maximum covering location problem. And I have P facilities that I locate, but I have this very binary criteria where you're either covered or you're not. And so instead of getting these distances from demands to the station, I get these rings around each of the station. And I try to get as much of the demand inside at least one of these rings. Right, so this is the one we'll mainly use today for our ambulance location problem. But I'll introduce all 4. Okay, so I'm about to introduce them with integer programming. Who's seen integer programming before? Who hasn't? All right, a couple of you. Hang in there with me. I'll introduce the models. If it's a little over your head, I'll have a picture to illustrate what's going on so you can at least understand the strengths and the weaknesses of the models. And you can come back to it later on after you've taken more classes. All right, so we have some notation here. This is the data. Now different models won't use all of these data points, but we'll start with this. So all of our models have a set of customers, I, and a set of potential facility sites. And we have P, quite often we have P facilities to locate at those J facility sites. Right? So these are the fire stations that we have in existence. At any given shift, you're not going to have staff to cover each of those stations. You're just going to pick some of them. And that's the idea here. All of our models have a demand for each customer. So this we could collect historically. We could look over the year. How many 911 calls does this neighborhood generate? And that can be considered a single demand point. We have a cost to transport one unit from facility site J to our customer location I. This is quite often the distance or travel time. And for one of our models, we'll have a fixed cost to open a facility. And so we have to make it like an annual cost. So we can match up our fixed costs with our transportation costs. We're locating P facilities. And in our coverage model, we have to say what's covered and what's not. And so for each one of our facility sites, we have a subset. V sub I is, or for each one of our customers, we have a subset V sub I, which is the set of facilities that covers it. And then our decision variables for the models are location decisions. So xj is 1 if we locate facility J, and 0 otherwise. And then we have the allocation decisions, yij, which is 1 if facility J serves customer I, and 0 otherwise. All right, our base model that we'll look at is the uncapacitated fixed charge location problem. And if you're looking at the models, this is sort of the one that doesn't belong, and because I don't give you exactly P facilities to locate. Okay, we get to determine what that level is, and typically we know what our staffing level is. But this is still a good model to look at. And in this model, our objective is to really minimize our cost. So it's minimizing our fixed costs. I don't have a pointer here, I'm not tall enough. But our fixed costs are this first term here in our objective function, the fj, xj. So we have to pay that fixed cost for each facility that we open, and there might be a different cost for different sites. And then we add on the demand-weighted cost for responding to calls based on our allocation decisions. Right, so we've got this fixed cost and this transportation cost. And so we want to lower our transportation costs. This is where we can open a lot of facilities, but lowering our second term in our objective usually means a bigger fixed cost. So we want to balance the two and find the sweet spot. Our only criteria is that we assign each one of our demands to exactly one facility that's open. Okay, so this is our allocation decision. And we only can allocate a facility to a demand location if that facility is actually open. Right. And then we have binary variables. Any questions about this? Just a side note, if you're following along with integer programming, it's always optimal to assign each customer to its closest open facility. Right? If not, we could always reduce our costs by sending it to a closer open facility. All right, our second model is the p-median model. It is very similar to the first model we had, except now we have exactly P facilities to locate. All right, so we've got the network, and I have 5 ambulances at the shift, pick 5 of the open stations. So our objective only has that second, that minimize the demand-weighted distance term that we saw in the first model. And this is our transportation cost. It could be minimizing the average travel time, for example. Again, we have to satisfy all of our demands, so every customer has to be assigned to the closest station, and it will be the closest station. And we only can assign customers to open facilities. And we have our binary variables down here. All right, so I have a picture of this. The lines might be a little bit light, but this is just an example with some open stations on a network of what a solution may look like. And you can see that all of the locations are sent to the closest unit. I didn't assign demands to these points, but you can see just by inspection that some of these points have a lot of lines going into them and others not as many, right? So if I'm modeling service networks, I might be concerned with that. One thing is that service providers don't want to do too much work or too little work. If you've done a ride-along, they get bored if they're not responding to calls. They want to practice their skills. They want to save lives. They want to make a difference. But it can also be, on the flip side, it can be very exhausting if they never really get any downtime. It can be very mentally challenging to just respond to all these calls and deal with a lot of emergencies and not have a little time off in between calls and just always be on the go. And so that the base models might introduce an inequity from the service provider point of view that we don't really like. And that's something we might want to keep an eye on. The P-center model is similar to the P-median model, except I don't like it at all, and you'll soon see why. And what we do here is we're minimizing the maximum radius here. So this is like the worst case customer, right? We want to make the worst case not so bad. And we're no longer considering our average customer at all, and we're actually no longer considering the amount of demand. So our first 2 models considered demand-weighted distance, and they said, well, if you produce a lot of calls at this location, then we want to really take that into account. And we looked at our average demand-weighted distance. And here we're not considering that. We're just looking at the worst case. And so we minimize the maximum radius through this guy up here, our first set of constraints. So for every customer, we look at the distance to its closest, to its assigned station. And we set that less than or equal to r. So we want to minimize r. But r has to be bigger than all those distances that we had to stations. And so we're still locating our P facilities on our network, just as we did in the last model. We still have to assign all of our customers to an open station, and it has to be an open station, right? So these three sets of constraints are the same. We're only considered with, one of our customers. And I don't know which customer is going to be the worst case. That's what we're going to solve for. We want to minimize this worst case scenario. Okay, so I have a picture here. So if I took our previous model for the P median, now this would be our value R right here. It would be this worst case distance. Right? And I don't care about the average service. I don't care about the average patient's experience or the average waiting time. I'm only concerned with the worst case. Okay. Needless to say, this isn't used very widely, especially in public sector applications where you actually want to do the most you can with what you have. And kind of the average experience is pretty meaningful in some of these applications. All right, and so our last model that we'll talk about, at least looking at the canonical facility location models, is the maximal coverage formulation. So this one looks a little bit different. We actually have some new variables down here. So I'm not doing the allocation decisions. I'm not assigning a customer to an open station. I am just recording whether or not a customer is covered. Right? So I showed you those stations earlier and those rings around the station. If there's at least one ring around a customer, it's covered. So ZI would be 1, and that customer would be covered. And actually, all of that demand at that location would then be covered. Right? So we want to cover the areas with the highest call volume. Right, so our objective is to maximize coverage, and it's a weighted coverage. It's weighted by the demand. Our first set of constraints is to locate the P facilities at the station. So we still have the XJ variables here. And our second constraint is a little bit new. And so we have to somehow match our coverage variables to where we've located the facilities. And this, we have to have congruence between our Z variables and our X variables. So we say here that a customer can only be covered, right? So we're trying to maximize this. We want to set the ZI to be 1. Customer I is covered. If at least one of the facilities that covers it is opened, right? So that's the only way we can achieve that. All right, so this is our base model. We can design this V sub I to be based on this 9-minute coverage, right? So this is a great starting point. So I have a question at the bottom of this slide that we'll come back to of how do we adjust this base model to address ambulances not always being available. Right, so we're sort of assuming that every ambulance is available all the time, and that is a bad assumption. They're busy about half the time responding to other calls for service. So we'll come back to that. But first I want to show you a picture. I promised you a picture. So here's my picture with the rings again. All right, so we want to cover as many of these X's as we can by strategically locating these ambulances. Okay, so you can see that over here we're not covered at all. And other places where we've covered certain locations 2 times or 3 times, right? We don't get extra credit for doing this, right? So why might we want extra credit for covering certain locations 2 or 3 times? Exactly. Yeah, so the multiple coverage basically takes into account that ambulances aren't always available. All right, so that's kind of the key to looking at this, is we want to have multiple coverage models. All right, so how many layers of coverage? Well, it depends, but it depends on how busy they are. All right, a couple of backup ideas about facility location. So if you're a little confused by all the integer programming, this is a good time to sort of look at the models. So earlier I mentioned that some of the stations we might actually allocate too much of the demand, right? And so service providers can't give 110%. They only have so much time that they can spend responding to calls. In facility location models, most models have a capacitated version, right? And this is going to help us address that situation. So most facilities have a throughput capacity, and this is like an input. I only can handle so many patients per hour or per shift, right? And this helps us balance our workload among our service providers. What happens though is when we have that location allocation part, we might not be sending our customers to the closest station. Some of them might have to go to a further station to balance that workload. All right, but that's probably a realistic consideration for modeling service networks. That's something we want to take into account. It can also be a decision variable in certain applications where you might have discrete choices of how big of a facility you could open, and they might have varying capacities and maybe different costs too. Right? You'll see this implemented in a couple of different ways. And you could also potentially have a continuous variable if cost is a function of capacity. Right, so I won't introduce the capacitated models, but just know that that will help us balance our workload. It was very interesting in that I was talking with a Madison firefighter a couple years ago, and there was, there's always a summer construction. We joke in the upper Midwest, so we have 2 seasons, winter and construction season. And so there's some construction downtown, and we've got lakes and everything in the way, so it's hard to drive around. And what happened was I had to use a different station because there was too much construction around their main fire station that had too many calls assigned to it. And so they used a different station, and they found that it balanced the workload. And their staff was so much happier. They ended up just keeping that solution, even though it was sort of suboptimal from the response time point of view, that some customers might have had a slower response, but nobody was complaining, and their service providers were much happier. And so they saw that as kind of a good solution. And so we haven't taken into account the our service providers in our solution, but quite often we need to do that, and you run models, and your service providers will tell you what they don't like about your solutions. And then you have to add some constraints in and come back and rerun the model. So it's very important to do that with human service providers. All right, so I've got a uncapacitated version where you might have 2 stations that have too much demand, which means you have sad service providers. And you might want to rerun the model with a capacitated version. And the one thing to note here is that you would actually potentially open a different set of stations. So it's not like I'm just reassigning the demand to balance it all out. Balancing the workload might actually motivate a completely different system design to begin with. All right, so I introduced the base models. I talked about the covering models and how I like them, and they could be applied to locating ambulances. And we have this nice objective that is kind of this covering function that we can use in our coverage model. But I want to actually have something that's somewhat realistic. I want to cover most calls in 9 minutes. But I want to extend our model. So criteria 1 is the one that we'll talk about, which is the idea of backup coverage. I think it's the most intuitive. Ambulances are not always available, and so we need to have backup coverage in our optimization models. The second criteria is that we want our ambulances to respond to roughly the same number of calls. I told you the trick with that one. It's a capacitated models. We can add some constraints. The third and fourth constraints, I think we're not going to have time to get to today, but we can look at non-deterministic travel times. And we can also, if you're much more certain to respond within 9 minutes, if the call's within a mile or 2, than when it's a little further out. And the trick here is like a p-median model variation. And then 4 is different types of ambulances. Well, that's like opening a can of worms, so we're not going to do that today. But all of these things have been considered in the literature, as well as many more criteria. All right, so let's talk about backup coverage. I've got pictures with this too. I will stop to answer any questions that you have first. You have all been quiet, and I'm happy to talk. Any other questions? How are the response times in Norman, Oklahoma? Not good? Good. Yep.
In order to distribute the load on the facility stations, you added more facility, but why wouldn't, you're not considering redistributing demands on the current or the given station that you have?
Okay. So I missed the first part of your question. You said I added a facility, or
Yes.
I moved?
So you said one of the stations has
Was moved.
demands that are assigned to it.
Mm-hmm.
And you add one more facility in order to distribute the demand to reduce the load on
Oh, I see.
the stations.
Well, I thought the picture had the same number of facilities, but at different locations. Maybe I can't count, but that was my yes. But right, yeah. So you can do either one, but typically it's hard. You are very resource constrained in public sector problems. You kind of have to do the best you can with what you've got. So that's usually here's what the shifts are. right? And you can have the meta problem of how do I design the shifts at the right time. That should also be part of the analysis along the way. That's a good question. Anything else?
How would you account for like population growth and things like that? Like when you're figuring out where to locate these facilities, how would you plan for a demand that's not there yet but might be there in the future?
Oh, that's a great question. So the demand that's not there yet, but that could be in the future, that is something that you would consider outside of these models, and that usually that is a decision that's made when they zone the land, that they need to keep room for a station. That's quite frequently how you do it there. And so it's more of a zoning problem, and then that's available to you in the future. It's a problem when they don't do that, for sure. Sometimes the stations aren't where you want them to be, but quite often that's what happens in a lot of communities. There are other things too. I worked with an agency that had, it was very rural, but it was a vacation destination. And so they had like crazy seasonalities that were going on, and it was just a matter of making sure that they had the right staffing level and worked with their volunteers to get better coverage at times that were busier. Any other questions? These are good. You're on a roll. You have a question?
What do you do when you don't have the access, like with the roads? How do you solve that problem? Like, let's say there is a vacation place and you have beach, but you can access it with the ambulance car, but people
Okay.
need the assistance.
Oh, okay, so when there's not, you can't drive there?
Yeah, but there are like, do you place any stations there? Or
Oh, right. You can drive almost anywhere, I can assure you. There are sometimes helicopters that respond to trauma calls typically, but things are pretty accessible by road. Then when they might not be is after a disaster, when there are things that are washed away, and that's kind of a separate urban search and rescue problem, and it might have different types of resources. I've studied that a little bit, but usually it's been in the context of being able to drive on the roads and maybe just taking a longer route. Good question. Anything else? All right, I have all sorts of stories about ambulances, so at the end, if you are curious, you can ask me. Okay, so I've got some talking about backup coverage here. We'll come back to our covering model. I have a picture of a cat inside of a box backing up another cat. I like the cat in a box picture. It just reminded me of backup coverage. And incidentally, I have 2 cats, and one sort of is the backup cat to the other cat, because the first cat was getting kind of old, and my daughters were really attached to it, so we needed to get a backup cat. So Lucky's Hopper's backup. And they're both still around, and they're doing great. All right, so I want to talk about a couple of key ideas that exist out there for coverage models and backup coverage. So this is actually pretty critical. Basically, we had we had 4 models, our 4 canonical models. The first 3 looked at kind of match a customer with a facility. So we actually make an assignment. This customer is assigned to this location. Okay, so that was our uncapacitated facility location problem, our P-median problem, and the P-center problem. The 4th one was different. It was the covering model. It had the rings. And we didn't actually make the allocation decision. We just looked at if a station was located within the ring around me, that I'm covered. Right, so that's what we're gonna start with here. So we had this variable. It was ZI is equal to 1 if customer I is covered. It could be covered once. It could be covered 2 times. It could be covered 3 or more times, right? Backup service is actually really important, and it's kind of obvious. You know, our first choice decision is pretty obvious. Our backup choices are less obvious, especially when you want to balance the workload, and that's actually why optimization is actually pretty useful for some of these applications. All right, so we have to look at our backup coverage, and to do that, we're going to actually count how many times we're going to be covered, a location is covered. So instead of our ZI is going to be equal to 1, we'll say ZIK is going to be equal to 1 if a customer is covered at least K times, okay, and 0 otherwise. So now we'll have degrees of coverage. So if you're covered twice, you're also covered once. And this is the idea here. All right, so I've got a variable up there at the top that's just copied from the last slide. So we can have an example. Let's say K is equal to 2. If a location I is covered once, then ZI1 is equal to 1. We're covered once, and ZI2 is equal to 0. And our second line here, if location I is covered twice, ZI1 is 1. Even though we're covered twice, we're also covered once. And then we're also covered twice, right? So both of our variables here are equal to 1. Okay, so how do we maximize, our coverage if we're going to consider backup coverage? Well, there's a lot of different options. Some are better than others. We'll talk about 3 base ideas, and this will get you thinking about backup coverage. The first is we can actually maximize double coverage and not even consider single coverage, right? Just take that as a given that most customers will be covered once. Not my favorite, but we'll introduce it. The second is we want to have a weight. So to get full coverage, 100% coverage for that location, you need to be covered once and twice, right? Otherwise, you just get partial credit for single coverage if you're not double coverage, and the partial credit you get is theta. So let's say theta has to be greater than 1/2, right? It's most important to be covered at least once. And then we have 1 minus theta as our weight for double coverage. And the third one, we'll kind of look at the problem and say, well, there's a certain amount of time ambulances are busy. Why don't we use that to inform our model? And that will actually inform our value of theta. Right, so we're going to see a lot of coverage models, and I'll show you the coverage picture and what it looks like. Okay, so I am not tall enough to reach that at the top, but we're going to maximize our double covered demand. So it's weighted by the demand at each location, which is HI. And our variable ZI2 is 1. That variable is 1 if we're covered twice at that location. So if you look through this model, you'll see ZI2 in a couple places, but you'll never see ZI1. We don't care about single coverage, so it doesn't show up. All right, so our first constraint up there is to locate P facilities. Okay, so that part's the same. I think I can reach this one here. So this is our definition of double coverage. It looks like our definition of single coverage, except I'm adding a 1 here. And this requires, I only can have double coverage if I have at least 2 facilities that are open within my radius. Okay, so that 1 kind of removes the option for single coverage here. And then I have the same binary variables down here at the bottom. Okay, so the problem with this, as you can come over and see, is that if this were our solution, we'd get credit for responding here, kind of in this area, and then over here. All right, so only locations covered by at least 2 circles. They can be covered 3 times. That's cool. I'm done with that. But if they're just covered once, now I get 0 credit. It's like I'm covering them not at all. Okay. I don't like that. I think you should get some credit for covering some of these locations. All right, so we can see the limitation of this type of model. Okay, so the extension to this is pretty intuitive and probably one that you'll like a little bit more. And this is where we'll weigh the single coverage with double coverage. So now we can get full credit if we have double coverage, but we still get partial credit for that single coverage. And so our objective function weighs our single coverage, which is HI/ZI1 by theta. And then we add the double coverage to that. So that's the second term up there, which is the 1 minus theta times the sum of HI/ZI2, right? So theta plus 1 minus theta is equal to 1, and that gives you your full credit. Okay, so we do need theta to be greater than 1/2 to make this all work. So the only thing that's different from the last slide is this constraint. So ZI1 plus ZI2 has to be less than or equal to the number of stations that are open within the radius, right? And so if only one of those is open, we want to force ZI1 to be 1 to give us credit for single coverage. And if theta is greater than 1/2, that'll make that work, right? Automatically, based on our objective because we're maximizing. But actually, that's not required here because you have the hierarchical coverage. I forgot about this guy, where ZI2 has to be less than ZI1. So you can't have double coverage unless you have single coverage. But in general, you want more credit for single coverage than double coverage. And so here you can see that we get a lot of partial credit for all the single coverage that we sort of lost on the last model. And it gives us an incentive to double cover the most important areas of the region, which is the parts of the region with the highest call volume. Any questions or observations? Does anybody like the first model more than this one? No. Okay, I was going to ask why, but there will be no explanation. All right. Okay, and the last model moves us from a covering model to an expected covering model. Does everybody know how to take an expected value? Take an average. Okay, you will have to take us an expected value here, but it's pretty simple. And this really is looking at, on average, what do we expect our coverage level to be, right? So if we were to look at a real system, we'd have to look at the call volumes being different. So we've already taken that into account. We'd also have to look at how frequently we'd need to call backup coverage. And so we'd have to relate that ambulance busy proportion to our model in some way, right? And so that's what we want to do here, is we want to come up with a data-driven way to estimate our theta. Okay, so in this case, sometimes we might have to be covered 3 times or more, right? We might go, our first and our second choice ambulance might not be available. And so we'll take that into account. And now we have a ZIK, which is our variable, which says, which is 1 if our customer I is covered at least K times, right? So how many times can a location be covered? Well, I'm locating P ambulances on my network, so it can be covered up to P times. All right, so I promised you that we're going to take an expected value, and so we're going to estimate our theta by considering this value E sub K, right, which is the, at location I, if it's covered K times, then we want to look at how much of that expected demand is covered based on whether the ambulances are busy. Okay, so I'm going to make a big giant assumption. It's probably not going to hold in reality, but let's say it's good enough for practice. And I'm going to say that, or I'm going to assume that all the ambulances are busy about the same amount of time. Right, so I told you the trick to how to kind of get that to work out in reality. And I'll say they're busy some proportion Q of the time. So maybe it's like 30%, maybe it's 50%. Ambulances are usually not busy 90% of the time, because otherwise they would never really be available for that next call. Okay, so now we have this statement here. So if this ambulance is covered, or location I is covered K times, I want to look at the expected covered demand. Well, I'm going to weigh it by the demand here, and then I look at the probability that it's covered, right? Which is just 1 minus the probability that it's not covered by those K ambulances. Which is just 1 minus the probability that all K ambulances are busy. They cover it. Which is just 1 minus Q to the kth power. All right, so we can just use some simple probability in here to get this estimate. Like we saw in the last model, we had coverage, and then we looked at the extra coverage that we get for double covering. And that's called the marginal contribution of double coverage. And here we're going to consider coverage up to K times. But we're going to look at that marginal improvement by covering it 1 additional time, which is just this EK minus 1, which gives us this expression here, right? So it's the fraction of the demand times the probability that it's covered the kth time, which means the previous our first K minus 1 ambulances were busy, and then our last ambulance was free. Okay, and this can be thought of as our theta K. And it's also decreasing in K, which is kind of a nice observation. And we can use this in our integer programming model. And it looks very similar to the last model that we looked at with double coverage, but it reflects more the system dynamics and the queuing dynamics that are going on in the background. All right, so that's what we have here. And so that's what we have in the first line is we're maximizing our covered demand, and this is the expected coverage in this case because it's taking our busy probabilities into account. So it's always the amount of demand at a location, and then we look at how many times it's actually covered. Okay, we're still locating our P ambulances at our various locations. And here this actually is a constraint from the last model with double coverage. So all of our variables covering it once, covering it or at least 1 time, plus covering it at least 2 times, plus covering location I at least K times has to be less than or equal to the amount of stations that are covering that location. And then we have binary variables. The part we lost was that hierarchical coverage model. So if you're still with me at this point, we have our objective coefficients are monotonically decreasing, so we don't have to enforce that hierarchical coverage. It will automatically be taken care of with our optimization with the objective function. Okay? So this model came back in 1983, and it's still kind of used as and widely cited today. I've cited this paper many times, and it's a great way to understand how to locate service providers on a network, given that the service providers aren't available all the time. All right. So that's all the models I'm going to introduce. I introduced many, many integer programming models. I give you a taste for some of the applications I've worked on and what I've done with some of the service providers. I would be happy to answer some questions that you have about the theory or practice of emergency medical services. Mm-hmm.
So I had a question about how does this look like to the EMS users and operators? Do they have all the models available to them through a tool, and they can have multiple options as to how to select the response? Or do they have a designated model that they're using? I don't know if that
Oh, okay, yeah.
That's what I'm asking. Like, how do they, because there's different ways to decide, right, to make
Right.
decisions. So are they have all those different tools available to them, or do they have one set?
They are not running enough integer programming, I'll tell you that. So what they do in the software, and so this is kind of crazy because the systems are very much at the local level, and so they don't have like a shared software. But most of the software that they have is about who to send to this immediate call for service. The planning decisions, it's anybody's best guess, you know. And usually they're pretty good at math, and they can kind of figure out local optimization and making some tweaks, and they get enough calls where it all balances out. But they do have some choices, and yeah, in general they could be doing some more. Some of those models that I introduced from the 70s were used they were still being used on 9/11 to locate fire trucks. It's like once they have a tool, they just keep using it forever, even if maybe the assumptions could be improved by further models. So the answer is it depends, and a lot of different things are done in different places.
So do different locations, different cities use different priorities? Because you mentioned
Mhm.
that pretty much they're all measured by the same metric,
Yes,
but they all have different ways in which they make that decision.
definitely, to actually do the actual staffing and where they're locating. And in my evening talk today, I'll talk about other things. Sometimes some communities locate at street corners and they relocate them on the fly. And so they're not really choosing stations that they're going to go back to. And so they'll need a completely different set of models to support that. So that's interesting. Yeah, but there are a lot of good tools out there to make informed decisions. So some of the work that I've done is actually talking about, is the staffing level correct? Are the locations that they're using correct? How could they be improved? And you can just run some simple models and give them really important insights. Mm-hmm.
For a lot of OR models, we worry about the problem getting too big.
Mm-hmm.
But in reality, for a lot of these kinds of models, small problems are too trivial.
Right.
So, I mean, you could use someone with expert knowledge to figure out, if the town is small enough.
Right.
So at what point are they do they start becoming usable? Does that make sense? Like what's the demand that ends up making these problems needed?
Okay, that's a good question. Yeah, so it's usually the total number of ambulances, and most communities have like fewer than 6 ambulances on call at any given time, except for the bigger cities. What makes it much more difficult is they have different types of vehicles available, and then you have to find the right mix, and then you start looking at prioritized customers, and at that point it becomes much more difficult to look at. So some of the cities will have all paramedic fleet, and they can be indistinguishable servers on a network, kind of like what we typically assume in operations research. But in reality, they have a mix of vehicles. So even smaller problems could become non-trivial in those situations. That's a good question. Mm-hmm.
Can these models be used to design the Uber or Lyft cab system so that we can get the cabs within the stipulated time?
Yes and no. So you don't send the Uber or Lyft to calls. So you don't really have that allocation decision. You just provide prices to incentivize them to move in certain ways. But it's, there's a lot of the similar ideas that I think go over there. But the work staff is managed in a very different way. That these models provide some insight, but they would really need to be changed to be able to apply in those situations. But yes, I think a lot of vehicles on a network and having like response beats. So even if you're not at a station, if this is your beat and this is your neighborhood you drive around, if you're a police officer, these models are a really good starting point for many of those applications. But as you can see, for any particular problem, you have to list your assumptions and then start making changes to the model so that those assumptions match your reality. You could locate the shared bike hubs. Nobody mentioned that, but I noticed that you had the bike hubs around here.
Any other questions?
There's one over here.
For other reasons, does it ever make sense to locate two ambulances at the same space, like
Yes. Yeah.
facilities and stuff? But none of the models.
None of the models consider that here, although they can be, you could just make a copy of a model, or I'm sorry, a copy of a station here, so they could consider that. No, that was one of the things that it's not obvious to service providers, and so that's one of the things I've discovered as I've talked to them, the county that I've worked with the most in the past, they needed 2 ambulances at a station, and it was very surprising to them because it wasn't a ton of demand there. It was clearly they needed 1 ambulance, but it was so important for backup coverage, that location, that they needed 2 ambulances, and that was sort of a counterintuitive result for them, and it was helpful. Very good question. Yeah, you would never need 2 ambulances at the same location if you weren't considering backup coverage.
Okay, thanks a lot.
You're welcome. Thank you.